All right. Thanks for the introduction, and thanks for the organizers, and especially thanks to Aurelia for inviting me here and having me here for this workshop. Really loving it with the program. I'm already looking forward to all the activities that are ahead of us. So I want to take the next few minutes to talk you through a little bit about how can we speed up CMR, but now with a focus on how can artificial intelligence help us here, really going from the workflow, from the acquisition to the analysis. And I want to talk about these various different aspects of starting with view planning and the image acquisition, going over to image reconstruction, then followed by image analysis. And since we know motion is a big deal in cardiac MRI, respiratory and cardiac motion, I want to also take a moment to talk about that. And then wrap it up by looking at some methods that look at quality assessment and the final diagnostic. So we'll not have time to go into full detail in all of these different aspects, but if you want to know more about this, this has been extensively studied in 3 member-initiated tutorials which I hosted together with Teresa Correa at the ISMRM in 2021, 2022, and also this year in our Cardiac MR Rodeo, where we have challenged all from the technician to the clinician to the engineer to the computer scientist to give their view on how we can speed up the whole thing. This is all compiled in our website, and if you want to read more there, we have also put out a review paper about these things. So let me start off with the view planning. We know that we ideally want to have an automated planning, since we have a very elaborate protocol which we have ahead of us. So an AI-assisted view planning, as already Matthias was showing, like instead of like manually dragging around all the different slices and locations of getting the different views out, we want to have an assistant viewing that helps us in the landmark positioning. On top of that, during scanning, we need to be prepared for any irregularities, any changes that can happen in the respiratory or cardiac cycle due to arrhythmias, for example. So we need to be able to, on the fly, change our acquisition protocol. And one way of doing this, and this is slides I got from Olivier Schubert from the UCL group in London. They worked on real-time assessment and adjustment during cardiac stress perfusion. So they have a very fast network that is able to reconstruct from this highly undersampled data an image, and this is then paired together with a segmentation network to get out then the functional parameters, which they can display here on a beat-to-beat scale, the different stroke volume, and then they can see if they when they should start targeting the imaging and the stress load. Also work here from the group in Lyric, which was shown at ISMRM this year, is an automatic identification of the inversion time. So also here you have an automatic cardiac localization, you have a segmentation, and then you find from your whole TI series the best inversion time to forward this then back to the next sequence. And you can also take this one step further in terms of scan parameter adjustments. This is work from Martin Terpstra. This is not yet in the heart, but just want to give you a little bit of a feeling of where the field is going. We can also have, like, if we think about the quantitative and fingerprinting sequences, we will always need to change for the right TE, TR, flip angle timings. We either set them a priori based on our knowledge, but also we can have AI to help us drive this in kind of a reinforcement learning strategy. We have an agent that acts then on the scan parameters and that adjusts this either on the real time or based on some prior sequences. And this is doing very well in terms of SNR and CNR recovery, as he shows here in the Phantom. Now, let me talk a little bit about image reconstruction, which is a huge deal and which was like one of the first things that people looked into when we were working on deep learning applications for CMR, and different flavors on how you can do your machine learning based image reconstruction. This can be either This can be either an image enhancement where you have your undersampled case-based input and you have your conventional reconstruction, or a joint operator that gives you then an initial image, and this image goes in through your neural network. You can have this in a physics-based unrolled fashion where you have iteratively unrolled all the different networks and you take as input the noisy image as well as your case-based and cause sensitivity maps for data consistency. You can also do it directly in the case base itself. So you're learning directly from the undersampled case base to a fully sampled case base in a similar fashion as Grappa is doing. Or you learn some deep image prior or plug and play prior. So you have some a priori knowledge that you're trying to distill, some denoising tasks that you're trying to learn. And you can plug this into your either conventional reconstruction or into a deep learning reconstruction, whatever flavor you want. In the last few years, there were a lot of distributional learning methods coming up, like diffusion models, which are trying to model the inverse problem, going from the noisy noise representation to the image and intermittent into that. We have more recently now seen also that we can integrate data consistency for that. I want to talk to you a little bit about the physics-based unrolling, and this is work I've been working on during my time in King's College in London, where we have here directly this unrolled method. So we have here this unrolling of the different iterations. This is a regularizer, which we're trying to learn then with intermittent data consistency steps. And for this special application, we have 3D cardiac cine. So we are separating then also these 3D and temporal dimensions into a 3D convolution on the 1D, 3D spatial and a 1D temporal convolution. But in principle, what always underlies these unrolled optimizations that you need to find your lower level problem. So I need to kind of like decide on kind of what regularizer do I want, in which way I want to structure here, regularizer and data consistency in sequential and parallel. And I also have on top of that my higher level problem. Do I have, am I in a supervised training scenario? Do I have fully sampled high resolutional data so I can compare directly with a mean squared error? Or am I in a different setting where I only have weak labels, or maybe have only labels that are driven directly from the network reconstruction? So what you can do then with this in this supervised scenario, I show you here on the top the images which we get out with this 3D sequence in comparison to the conventional 2D cine in two different flavors, in a very short threshold of around 7 seconds, or in a 2-minute free breathing and free running acquisition. The nice thing is what we are interested in was the left ventricular functional assessment, and we saw a very good agreement in terms of the ejection fraction of the 3D cine to the conventional 2D cine, but in a shorter acquisition time overall. So this was all done in a supervised manner. So now what happens if you may not have always fully sampled ground truths available? And this is work from from Mehmet Aksakaya's group, where they showed you can also split up the strategy on how you utilize your data. So you have your acquired case-based locations here, and you split them up into two sets. One set you use in your data consistency, and the other set you use in your training loss metric. And by that, you're driving the network itself to readapt to the different scenarios, because it's these disjoint sets of sampling masks. And by that, you can enforce some self-consistency or provide here a self-supervised learning. And they've shown this in two different applications. In a first-pass perfusion, where they also on top of that modeled the variance signal intensity, which we get from the perfusion as shown here, and compared it to a low rank and sparse reconstruction, a split slice Grappa. And they also used it in late gadolinium enhancement, where they could show that they can get an increase, like a 2 times faster acquisition without making any compromises in terms of image quality, which helps us again to speed up the acquisition side. We have also looked into this work from our group, which we also presented this year at ISMRM. What can you do if you only have access to undersampled data, and on top of that, to maybe even highly undersampled data? So we came up with this approach, which is a 2-step way of performing a contrastive self-supervision. So in the first step, it's again based on a physics-based unrolled network. So again, you see here these different iterations. We have again a UNet as a learned regularizer. But now we are trying to learn and embedding in the bottleneck by the contrastive learning. And this tries to maximize the agreement between similar looking sampling patterns and minimize the agreement between completely different sampling patterns. And by that, we get a better jump start of the network if we use this then in a self-supervised learning way, because again, we have no access to fully sampled ground truths. And we can plug this in then the information during the actual self-supervision stage, and then drive this with also with a self-consistency loss in case-based, cross-case-based loss and image loss. And what you can see here is our first results of a patient with active myocarditis, where we see that we can even push the acceleration factor quite high without very minor or little compromises in terms of image quality or residual error that we are seeing. So giving us a very good promise of we can leverage now a lot of more data, namely just the undersampled data, which we may be acquiring also on our daily basis, and get access to a larger database than at the end of the day. This brings me now to the next step of image analysis. Once we have then the image, we want to derive further information from there. And this is a slide I got from Jesse Hamilton, where they looked at cardiac MRF. So they're trying to learn a network to predict then the T1 and T2 maps from this highly undersampled time series. So they get here these fingerprints for each of the voxels, and then they have learned a network that was also trained for different RR interval timing. So instead of always then readapting your dictionary or recreating a dictionary after the scan, they already have it trained into the network, and then this fully connected neural network estimates then T1 and T2 values for every voxel location. And this works also very well. Here they show the comparison for the dictionary matching, which is the conventional way, let's say, and then the neural network, which shows very good agreement, and only with minor errors here in the lung area, but particularly in the heart region, where we're interested in very low errors in both T1 and T2. Also, cardiac segmentation is a very important aspect. So we want to get out left ventricular functional parameters. So we need to segment the left ventricle and the right ventricle. This is early works from Wenjia and many other groups have worked on that as well. We have also worked on vessel segmentation and shape analysis, so automated tracking of the aortic branch in the abdominal and thoracic area, and then also performing some aortic diameter profiling to identify any risk factors there. But what we have seen more lately is that all of these networks are now more moving towards joint networks, where we try to bring everything together. And this is work by Chen Jin, where she looked in combining now a segmentation network down here with a motion estimation network, either one of them benefiting each other. So since we have the underlying cardiac dynamics, we can make use of them and inform the segmentation network of it, but also the clear and sharp boundaries of the segmentation mask can inform the motion estimation network, that we don't have any motion fields that are unnaturally pointing outwards of, for example, the myocardium. So this brings me now to the motion aspect, which is very important. And here we can do different flavors. First, I want to talk you through the pairwise registration. So, and this done in the image domain. So let's say we have pairs of images from, let's say, end expiratory to end inspiratory, for example. And this is a diffeomorphic network developed by a previous colleague Haikon Chi at the time at KCL. But there are also different other networks out there. Just to give you a few names. And also, I've been working on case-based registration. So instead of formulating or trying to solve this in the image domain, where if you think about the highly undersampled case, you might be obstructed by the aliasing artifacts. Why not directly extract this information from the case space itself? And this is the so-called LIP-net, which we came up, which provides you with really nice motion fields directly from highly undersampled case-based data. And I also want to point out there are also other methods like the MR motors, which are also doing this, directly extracting this information from highly undersampled data. You can also do this in a different fashion, in a group-wise, since we know we have different dynamics or let's say more temporal information available to us. Why not use them directly? And again, here different networks that have been developed, the MRAFT, GMA raft, on which we are currently working, my PhD Ayagul on that, and a group-wise registration network where again you match to either some template or to a specific time point within the series, but you make use of the whole temporal dynamics of all the moving images that are going now into the registration. And you can use this information now to pair it with other networks. I already showed you the example for pairing it with a segmentation, but you can also pair it now with a reconstruction. So you have your initial reconstruction that are estimating now the motion fields from this highly undersampled data, and then you plug this all in, the motion fields and your undersampled data, into a motion compensated reconstruction. And what this allows us now, and this again is the work we are currently working on with the GMA raft, is that you have this highly undersampled data now with different trajectories. There's a Cartesian and a radial imaging, and you get still very good motion fields out that are quite reliable. And whereas the other deep learning-based methods and also conventional methods are really struggling in this very highly undersampled scenarios, and even giving you, I would say, non-realistic motion fields out that is happening here. So lastly, I want to talk about the diagnostic options that we have available. And due to time, I only want to focus on one aspect, which is the automated quality control. Once we have the images, and we still need to ensure that what we are getting out is also the right thing that we are actually targeting. And this is what we will also see more baked in to all of these different networks. We can have all different kinds of quality control mechanisms. We can have uncertainty measures in our reconstructions. We can have like unnatural flow fields that we can estimate or know that is the maximum amplitude, what kind of displacement we can expect. So just here give you a little bit of flavor. This is work from Daniel Ruckert's group, where they have looked for the UK Biobank in this very large cohort. Instead of going manually through all the cases, can we find a way to automate this process? And they were particularly interested in finding the right heart coverage. Was there any interslice motion happening? And then overall, was the image contrast sufficient to perform then the subsequent segmentation, because they wanted to use it then for the left ventricular functional assessment. So you could sort it in this optimal and non-optimal way. And this is already quite helpful that you can relook at the problematic cases. And then maybe either, if we want to close the loop again, adapt your imaging acquisition while you're already on it, or maybe you can change to a more robust reconstruction mechanisms for that. So to wrap it up, we're still having a lot of key challenges ahead of us in CMR. And so far, all of the methods that I just showed you here, they were primarily application specific and very much tailored to different solutions, like a cardiac cine or targeted for LGE imaging and so on. And most of the time, we have very limited feedback to the actual user about the processing that is actually happening, and what we and how trustworthy the actual AI processing is, and also then to the sequence itself. So really closing the loop between all of our nice speed up reconstruction analysis things that we could maybe infer a better imaging strategy than for that as well is still on an early research stage. The reliability and generalizability of these results is then, of course, questionable if we come to domain shifts. And this is an important thing which we really need to look at. So if you think about the changes in terms of population, in terms of disease prevalences, in terms of the selection strategy that you have chosen for setting up your training set and your validation set, also in terms of the imaging hardware that we have used, different vendors, different scanners, high field, low field, all of that mixing together makes a huge impact on how the networks can behave. And they can also, there's quite a large risk that there can hallucinations happening. And this is very risky, which we really need to look in now into the future more. But I think there's a change of a paradigm here. We see that we can help these networks by combining several multiple processing steps to make them more robust, to make them also more aware of these different domain shifts that are happening. And this will help us then to hopefully better integrate them into the workflow, where we also can have this more immediate feedback that allows us then to also intervene in case something really horribly would go wrong. So in summary, we have come from a past of, like, say, low-dimensional machine learning towards more in the present where we are to higher dimensional machine learning with more joint applications, network merging together, more informing each other together. But in the future, I think where this will all go to is that we also bring the human more back into the loop, that we have more multi-purpose and more generalized models that allows us also then to have a better integration into the workflows. With this, I would like to thank you very much for your attention, and I would like to thank everybody who gave me slides for the talk. Thank you.